In this presentation, I am going to explain slip power recovery scheme of speed control of slip ring induction motor. In that one, I will be specifically explaining what is static kramer drive system. Coming to slip power recovery scheme of speed control of slip ring induction motor. If PG is the air gap power, that is the power that is transferred from the stator into the rotor circuit, that's air gap power PG, and that is equal to S times PG plus 1 minus S times PG. And 1 minus S times PG is the component that is producing the mechanical power output. For PM equal to 1 minus S times PG. The remaining portions, S times PG is the slip power. Now, in rotor resistance control, the slip power is being wasted in a rotor resistance, and thereby you are controlling the speed of motor. Now, in slip recovery scheme, instead of wasting the slip power in the rotor resistance, it can be controlled by a converter, and that can be fed back into the line, and so that the efficiency is being improved. Therefore, rather than dissipating this slip power in the rotor resistance, it is fed back into the grid. There are two methods, or the main methods of implementing this, and that are called static kramer drive system and static Scherbius drive system. Now, in this presentation, I'll be explaining static kramer drive system, and in the next presentation, I will be explaining static Scherbius drive system. Static kramer drive system, that is used for the speed control of slip ring induction motor less than the synchronous speed, or for subsynchronous speed control. Therefore, this scheme provides speed control of slip ring induction motor below the synchronous speed. Coming to the circuit of implementing kramer drive system, stator is supplied by a three-phase AC, and the rotor, that is the rotor power or the rotor voltage, induced voltage in the rotor, that is rectified using an uncontrolled rectifier, and that is through an inductor that is connected to the input of an inverter. It is a control converter. By controlling the firing angle of the inverter, the power that is injected into the grid is controlled. Therefore, there is a transformer that is linking the output of the inverter into the grid. And the turns ratio of the stator to rotor, that is equal to small n, and the turns ratio of the transformer from the source side into the converter side equal to capital F. Therefore, in a kramer drive system, there is an uncontrolled rectifier, and as well as there is a controlled converter, or that is working as an inverter. Now, rotor circuit slip power is converted into DC by a diode rectifier, and this inverted this power, DC power, is inverted into AC by a line commutated inverter. This is a line commutated inverter that converts this DC into an AC, and that is connected into the grid through a transformer. The inverted 50 Hz power is then fed back into the line through a transformer. Since the slip power is fed back to the AC grid, unlike dissipating in the resistance, this scheme has got better efficiency. This slip power recovery scheme has got better efficiency compared to rotor resistance control. For in kramer system, the rotor power is rectified using a uncontrolled rectifier, and that is inverted into AC by a by controlling the firing angle, and that is injected into the grid. By controlling the firing angle of the inverter, you can control the power flow into the grid, and thereby you can vary the speed of the slip ring induction motor using kramer drive method. Now, coming to the speed control using kramer drive. Now, the speed of the motor is controlled by inverter firing angle alpha. By controlling the inverter firing angle alpha, the speed of the motor can be controlled. And this is representing the equivalent circuit of an induction motor, in which this is the stator parameters and this is the rotor parameters, resistance and inductance, and this is the injected voltage into the rotor. Now coming to this N, which is equal to the stator number of turns divided by the rotor number of turns, or that is the stator to rotor turns ratio. And similarly, M is the ratio of the transformer from the source side into the converter side. Now coming to the mathematical explanation of this one. Now the rotor power, that is, or the rotor voltage, is rectified by an uncontrolled rectifier, diode rectifier, three-phase diode rectifier. Now what is the output voltage of this one? That is nothing but 3 VML by pi. That's base. The DC voltage, average DC voltage available at this here is equal to 3 times V maximum value of the line voltage divided by pi, or 3 times root 2 times, that is RMS value of the line voltage divided by pi, or 3 root 2 into root 3 V phase. Therefore 3 root 2 into root 3 into V phase divided by pi. Now this phase voltage is the phase voltage on the rotor side. In order to convert into the stator side, that is multiplied by the slip S into the stator voltage per phase divided by N, that is stator to rotor ratio. Therefore the voltage, that is average voltage available at the output of this uncontrolled rectifier, is given by 3 root 6 divided by pi into SB divided by N, that is VD1. Now where S is the slip and V is the, that is this V is the stator per phase voltage, and N is the stator to rotor turns ratio. Therefore this is the voltage that is available at the output of the uncontrolled rectifier. Now coming to this VD2, that is available at the input of this inverter VD2, because VD2 is a variable quantity that varies with respect to the firing angle of this inverter. Therefore in that one, the same fashion, if you analyze that one, the voltage VD2 is given by 3 root 6 divided by pi into V divided by M into modulus of cos alpha, where alpha is the firing angle of this inverter. Therefore this is VD2, that is the voltage available at the input of the inverter, and VD1 is the voltage that is available at the output of the rectifier. And there's a linking inductor that is connecting between the rectifier and inverter. Therefore by controlling the firing angle of this inverter, you can control the power injected into the grid through the transformer. That is done in Kramer drive system. In the previous slide, we have derived the equation for VD1 and VD2, and now if you apply the Kirchhoff's voltage law to this loop, because here plus and here minus, similarly here plus and here minus. Now applying the Kirchhoff's voltage law to this loop, and also we know that average voltage across the inductor equal to 0. Volt second balance, the average voltage across the inductor equal to 0. Therefore VD1 minus VD2 equal to 0, or VD1 equal to VD2. This voltage is equal to VD2, and substituting that voltage, that is 3 root 6 divided by pi into SV divided by N, that should be equal to 3 root 6 divided by pi into V divided by M into modulus of cos alpha. And then from this equation you can get the slip S equal to N by M into modulus of cos alpha, or N by M is defined as a constant, some constant as A into modulus of cos alpha, where A equal to N by M. And the rotor speed, as you know, that omega r equal to omega s into 1 minus s. Substituting the value of the s, omega r equal to omega s into 1 minus A into modulus of cos alpha. Therefore by controlling the magnitude of the alpha, you can control the speed of the induction motor. For example, if you make alpha equal to say pi by 2, even alpha equal to pi by 2, you will be getting omega equal to, this will be equal to 0, or the omega equal to omega s. That never happens. Ideal case I'm telling, that is correspond to synchronous speed. Therefore alpha equal to pi by 2. Similarly, if you change the alpha equal to say extreme, alpha is changing between pi by 2 and pi. In the case of, because this is working as an inverter, the range of alpha is between pi by 2 and of course pi. Therefore, if the alpha is equal to say near to pi or almost equal to pi here, then we'll be getting it is equal to omega or equal to 0. Therefore, ideally speaking, that is, ideally the speed can be controlled between 0 and synchronous speed by controlling the inverter firing angle alpha. But in practical case, the maximum value of the alpha is limited to 165 degree for safe commutation of the inverter. That's a line commutator inverter. For the safe commutation, alpha is made equal to 165 degree, so that the slip can be changed from 0 to 0.966 A, where when alpha is changed from 90 degree to 165 degree. That is, when alpha is changing from that one, slip can be changed in this one. Therefore, by changing the firing angle of this inverter, you can vary the speed of the slip ring induction motor, that is omega, can be changed. That is what is done in Kramer drive system. Continuing the speed control using Kramer drive. The drive input power is the difference between the motor input power and the power fed back into the grid. That is the net input power into the motor. But the reactive power is the sum of the reactive power required for the motor plus inverter, meaning that the reactive power is increasing and real power requirement is reducing. That is why the power factor is getting reduced. That is why in Kramer mode of speed control, here it has got a poor power factor. The power factor is less. That is in the case of Kramer drive. Now coming to the torque versus speed characteristics. This is the torque versus speed characteristics of a Kramer drive system. Again, it is a first quadrant drive. You can have a power flow only in one direction because one side is a uncontrolled rectifier. And here for different firing angles, the torque versus speed, that is for a given alpha, this is the variation of the torque versus omega. As you increase the alpha, the speed is getting reduced. Therefore, this gives a relation between torque and the speed of the slip ring induction motor using Kramer drive, in which you are varying the firing angle of the inverter from 90 degree, because the firing angle is in between 90 and of course maximum ideally it is equal to 180 degree. As you change the firing angle, the speed of the induction motor changes. Now I'm going to explain the torque speed characteristics. Torque speed characteristics of for different firing angle. For different already I explained the previous slide. Same thing only here. Torque versus speed for a given firing angle. Therefore, as for a given firing angle, as torque increases, speed is slightly getting down. Slightly getting down. The reason I shall explain later. And here, this is almost looking appearance. It is almost like a separately excited DC motor. As torque increases, speed is slightly reducing. Now, as the firing angle is increasing, therefore this firing angle as it increases here, as firing angle is increasing, for a given torque, the speed is getting reduced. Therefore, by increasing the firing angle, you can reduce the speed of the motor using Kramer drive system. Therefore, the torque produced is proportional to the DC link current. The DC link current ID is there. As ID increases, the torque produced by the motor increases. It's a linearly related. Now, the speed torque characteristics of a motor for different firing angle or the firing angle of this inverter is shown as here. Now, when suddenly the load requirement is increasing, with a higher load, what happens? As the load requirement is increasing, what happens is the machine is getting down. The machine speed gets down. As the machine gets speed down, here the linking current, that is ID, gets increased. As ID gets increased, as per this one, you can say that as ID increases, the electromagnetic torque developed by the motor increases. Finally, the torque produced by the motor will be equivalent to the load demanded by the load. I mean, torque demanded by the load, TL. TE is equal to TL. That is what is happening as load increases or as load changes. For a given inverter firing angle, that is for a given inverter firing angle alpha, the inverter input voltage VD2 remains constant. For a given firing angle, the input voltage to the inverter is constant. That is a function of alpha. Since alpha is constant, that input voltage is constant. Now, if for a given firing angle, as torque increases, what happens? As torque increases, now as torque increases, ID also increases. ID also increases. As ID increases, the drop in the resistance of the linking inductor, that is to balance the drop across the resistance of the linking inductor, the voltage VD1, that is the output voltage of the rectifier, that is VD1 will be slightly increasing. Voltage VD1 is increasing means that speed is getting down. That is, as gets speed is going down, that voltage is increasing. Voltage VD1 becomes increases slightly, meaning that reducing the rotor speed slightly. Therefore, that is why as torque increases for a given firing angle, the speed is slightly getting down. Slightly getting down. So instead of a constant one, slightly getting. That is because of this problem. Or this is the and static Kramer drive has one. It's a one quadrant operation. Only the power flow can be from the rotor side into the grid. The reverse power is not permitted. But in the next, I'm going to be explaining Scherbius drive system, in which the both direction the power is possible. Even braking also possible. But in this case, regenerative braking is not possible in the case of a Kramer drive system. And the speed control character is looking like almost like a separately excited DC motor. Now let us see a problem on Kramer drive. Problem is a 3-phase 460 volt 60 hertz 6 pole star connected wound rotor induction motor has the following parameters: RS equal to 0.5 ohms, RR dash equal to 0.4 ohms, XS equal to XR dash equal to 1.2 ohms, and XM equal to 50 ohms. Stator to rotor turns ratio equal to 1.1. And the source side to converter side turns ratio of the transformer equal to 2.5. The induction motor is controlled by static Kramer drive. The load torque is proportional to the speed squared, and its value is 1175 RPM at RPM, and the corresponding torque is corresponding to 1175 RPM. Torque equal to 750 Newton meter. If the motor is required to operate at a speed of 1050 RPM, calculate the inductor current ID, the DC voltage VD, that is VD, which is equal to VD1 and VD2, both are equal, and the delay angle of the converter or that inverter, actually it's an inverter, firing angle alpha, and the losses of the diode rectifier, converters and transformers and inductors are negligible. So this is a problem. Let us come to the solution. First, you calculate what is the angular velocity corresponding to the speed, the rated speed as 1175 RPM. Corresponding to that angular velocity is given by 2 pi n divided by 60. 2 pi n divided by 60, and that's equal to 123.05 radians per second. And what is the corresponding synchronous speed? Let us see the synchronous speed of the motor. That is omega s is given by 4 pi f divided by p, or 4 pi into 60 divided by 6 pole machine, and that's equal to 125.66 radians per second. Therefore, we found what is the omega s and what is the omega m1 corresponding to 1175 RPM. Now, as per in the problem, the motor is running, speed is reduced to 1050 RPM. Now, corresponding to 1050 RPM, what is the corresponding angular velocity? That is omega m2, which is equal to 2 pi n divided by 60, or that is equal to 2 pi into 1050 divided by 60, and that is equal to 109.96 radians per second. We found what is the omega m1 and omega m2. Now, in the problem itself, it is said that the torque produced is proportional to the square of the speed. Therefore, we can say that TL1 divided by TL2 is equal to omega 1 square divided by omega 2 square. And from that equation, you can find out what corresponding to this speed, that is 1050 rpm, what is the corresponding torque developed, or TL2 equal to, because TL2 equal to TL1 into omega 1 square divided by omega 2 square. Substituting that one, we'll be getting 598.87 Newton meter. Therefore, this is the torque corresponding to the speed 1050 rpm. Continuing the previous problem itself, at the speed 1050 rpm, you can calculate what is the slip. Slip is given by omega s minus omega m divided by omega s. That is equal to, we'll be calculating, it is equal to 0.125. This is the slip corresponding to 1050 rpm. Now, in Kramer's drive system, already we have derived the relation between slip and the firing angle of the inverter. Slip S equal to N by M into the modulus of cos alpha, where N is the stator to rotor turns ratio, M is the ratio of the transformer from the source side to the converter. And substituting N and M and the slip already we calculated, in that one, from this equation, cos alpha can be derived at, that is modulus of cos alpha is given by S into M divided by N, or that is equal to, it's equal to 0.284. You'll be getting it is equal to 0.284. Now, in inverter mode of operation, you know that always the firing angle will be more than 90 degree. It is more than 90 degree. Therefore, this is the modulus of cos alpha, or cos alpha will become, it is equal to minus 0.284. And corresponding to minus 0.284, the firing angle will be getting 106.5 degree. Therefore, the firing angle will be more than 90 degree, which is equal to 106.5 degree. Now, the voltage that is coming on the DC side as well as the inverter side, VD1 equal to VD2 equal to VD. That equation is given by that voltage at the input of the inverter, that is the DC voltage, is given by 3 root 6 into V divided by pi into M into cos alpha. Substituting that equation, you can get the DC voltage at the input of the inverter, which is same as the output voltage of the rectifier, that is equal to 70.57 volt. This is the voltage. Therefore, from once you get the voltage, the torque equation is given by torque equal to this voltage VD1 into that ID, that divided by slip into omega s. Substituting in that equation, only the unknown is, that is equal to the unknown is equal to, will be getting the what the current equation, the corresponding current is will be getting, it is equal to 133.34 133.3 amperes. That is the DC link current corresponding to this speed, or corresponding to this slip point. 0.125 is the slip corresponding to that one.